Historically, Chapter 6 causes many students a lot of stress. I think it's imperative to remember that everything that you've learned in Chapters 1 through 5 in Euclidean geometry was in a plane. It was all two-dimensional. In Chapter 6, we're moving into space. So this is just delving into some other types of geometry. And you are being asked to consider what that would mean to the existing system. So in 6.1, we learn different ways to determine a plane and some basic definitions of planes. On day 1 of the course, I did talk about a plane as being a set of infinite lines just side by side to the point where it grows into a two-dimensional surface. You can think of a wall as a plane or a floor as a plane. Any flat surface, however, it would have infinite length. If a line intersects a plane, that point of intersection is called the foot. And on the first day of class, we learned that any two points determine a line, ray, or a segment. So now, in this section, we are learning what determines a plane. And we are told that any 3 points will determine a plane. That's something that's just assumed to be true. It's a postulate. We're not going to prove it, and it's not a definition. We know that 3 points determine a plane, and any 2 points determine a line, ray, or segment. So thus, does it follow then that a plane could be established by a line and a point? It does. And if 3 points determine a plane, would it also follow that 2 intersecting lines would determine a plane? It does. We know 3 points determine a plane. If I establish a line with 2 of those points, could I now apply the parallel postulate, which is, given a line and a point not on it, there is one and only one parallel line, and then say that 2 parallel lines determine a plane? I believe I could. We have a couple of other postulates that we need to look at. If a line intersects a plane that does not contain it, then the intersection is exactly at 1 point. And remember, we defined that as being the foot. If 2 planes intersect, then their intersection is 1 and only 1 line. Now, this is a definition, and I know you're always looking for short forms, but in this particular chapter, I really can't give you any short forms. So you're going to need to memorize these as they are. You could use the symbol for perpendicular, but it is imperative that every single phrase be in here. So if a line is perpendicular to a plane, then it is perpendicular to every line in that plane that passes through its foot. And this is the phrase that most students will leave off. You cannot, because, for example, if I have a line in a plane and I have a line that intersects that plane, that does not pass where the line in the plane does not pass through the foot, are they perpendicular? Okay, so the line that passes through, let's call this A, is perpendicular to plane P, and line B here does not pass through the foot of A. Are they perpendicular? No, they're not. So line B would have to pass through the foot in order for those two lines to be perpendicular. If plane M and plane N intersect, where do they intersect? Well, if two planes intersect, they intersect in a line, correct? So we're going to call that line AB. A, B, and V determine a plane. Any 3 points determine a plane. So A, V, and B determine plane M. Name the foot of line RS in M. That would be point P. AB and RS. So AB is here and RS is here. Any two lines that intersect determine a plane. In this case, they determine plane N. AB and a point determine a plane in N. So here's AB, and it would have to be a point not on the line. So you could choose S or R. Both answers would be correct. It just asked for one, so you would only need to list one. Does point W lie in plane N? No, it doesn't. The way this is drawn, N is, even if I highlighted N, you wouldn't really be able to see it, but see how it's dotted? That is implying that it's behind plane M. Does line AB, line AB and which other line determine plane M? So AB, and then the other line would be BW. H. A, B, and V. A, B, V, and what other point are coplanar? You could say P, but that's on the same line. I would choose W. A, B, V, and what other points are non-coplanar? So they're looking at A, B, and V, which are in plane M. So we could choose R or S, because those are not in plane M. If R and S lie in plane N, what can be said about line RS? We can say that line RS lies in plane M. N is in Nancy. Here we're given A, B, and C lie in plane M. They establish plane M. PB is perpendicular to AB and PB is perpendicular to BC. Therefore, PBA and PBC are right angles because if two lines are perpendicular, then they form right angles. And we know that all right angles are congruent. Or if two angles are right angles, then they are congruent angles. AB is given as congruent to BC, and then PB is congruent to itself by the reflexive property. Therefore, the triangles are congruent by side angle side, lines 4, 3, and 5. And again, for organizational purposes, we probably would have wanted to move line 4 to line 1, and then shift lines 1, 2, and 3 down. That would have made it much more organized. And then we have congruent triangles. So corresponding parts of congruent triangles are congruent, and our triangles are in line 6. Can a quadrilateral cut out of paper and folded along its side, is this still a plane figure? No. ABC is one plane, BCD is another. So remember, when we studied quadrilaterals, they were defined as a plane figure. So now that definition no longer fits in space. Given planes M and N intersect in line RS, plane M contains R, S, and V, N contains R, S, and T, TS is congruent to segment VR, segment TR is perpendicular to segment RS, and segment VS is perpendicular to segment RS. Prove that TR is congruent to VS. So to begin this proof, I am going to start with this information. I'm actually going to make it smaller so I can get the whole thing in here. Then we were given TR is perpendicular to RS, and VS is perpendicular to RS. It's kind of hard to mark the right angles on the 3D drawings. We were also given that TS is congruent to VS. Now that's the hypotenuse. So I'm going to go ahead and establish that angle TRS and angle VRS are right angles. Because if segments are perpendicular, then they form right angles. So that's my right angle. And then my hypotenuse was given as TS congruent to VS. And then I can find the leg RS congruent to itself by the reflexive property, which then would make triangle TRS congruent to triangle VRS by HL. And my right angles are in 3, my hypotenuse is in 4, and my leg is in 5. Now I can say the corresponding parts, segment TR, is congruent to VS. Here we are asked to prove that ST is perpendicular to BD. This is a problem in 6.1, and if we only did 6.1 today, we would end up with a 14-line proof. But we've completed 6.1 and 6.2 today, so the proof is going to look a little bit different. To begin writing this proof, I am going to grab some of these givens So then, since ST is perpendicular to AB and BC, then ST must be perpendicular to plane M. Because if a line is perpendicular to a plane, then it is perpendicular to every line in the plane that passes through, then I can say that ST is perpendicular to line BD, because if a line is perpendicular to, a plane, then it is perpendicular to every line in the plane that passes through, don't tell your English teachers I shortened that, its foot. So that's one more reason for doing two sections today. And 6.2. If STR is a right angle, can we conclude that ST is perpendicular to M? Why or why not? Because if we think about it, here's a counterexample. Here's RT, and I could draw this as a right angle, so it's perpendicular to the one line in the plane, but not ST is not perpendicular to the plane. So that's why it has to be perpendicular to two lines in order to be perpendicular to the plane. So in problem 2, segment PF is perpendicular to plane K. If a line is perpendicular to a plane, then it is perpendicular to every line in the plane that passes through its foot. So that makes PK or PF perpendicular to FG and PF perpendicular to FH. And then if two segments are perpendicular, they form right angles. And then PG is congruent to PH is given. PF congruent to itself is reflexive. That's my leg. So the triangles are congruent by HL. My right angles are in 3, my hypotenuse in 4, and my leg in 5. And then the angles are congruent because congruent triangles implies corresponding parts of congruent triangles are congruent. If you found this video helpful, please like and subscribe. Smash that like button. You know you wanna. Come on, give it a thumbs up.